Welcome back. In this section, we'll be looking at some of the basic ideas behind calculus, the origin story of calculus. One of them begins with the tangent line problem. To start off with, we have to introduce the idea of a secant line. A secant line, that's just a line that crosses through our function in two places. So if I have some function f of x, and if I've got 2 points that happen to be on that function, and I connect those 2 points with a straight line, then that straight line would be called a secant line. And the slope of that line would be the average rate of change. This is something where we use this all the time. If, let's say, our function is telling us the position of an object, and if x is a particular time, then the average rate of change would be the average change in our position. In other words, our average speed. How is our position changing with respect to time? Of course, average speeds are nice to know, but what you're more interested in knowing is your speed at an exact moment in time. And for that, you would need to have a tangent line. A tangent line, that's a line that touches your function at exactly 1 point, and the slope of that line tells you the instantaneous rate of change at that exact point. The difference between the two of these, we can see this with the following example. If you had a function that measured where your object is after x seconds, then whatever rate of change we're talking about is a change in distance over time. In other words, it would be measured in meters per second. If we had a secant line that went from x being 2 to x being 3, then our average rate of change, our average velocity, would be the velocity that you would have over that interval from 2 to 3 seconds. But that wouldn't tell you exactly how fast you were going at exactly 2 seconds or exactly 3 seconds. As an example, of course, think about driving in a car. You might start out, and over a period of 1 hour, you might cover 40 kilometers, but that doesn't mean that your speed was 40 kilometers an hour for the entire hour. Maybe sometimes you were going a little faster, maybe sometimes the car was stopped. If you average out all of your speeds, maybe it works out to 40 kilometers an hour, but that doesn't mean that you were traveling at that speed the entire time. You'd like to know what is your speed at any instant in time, or in other words, you'd like to know what is the slope of that tangent line. So how can we solve this problem? A secant line is kind of easy because you have 2 points, and if you wanted to create a secant line, that's a Math 10, Math 11 problem, creating the equation of a line that connects 2 points, and then easy enough to find the slope of that line. So how can we get a tangent line from a secant line? The idea is we have these 2 points, we'll just get our 2 points to be closer and closer and closer together. And if that second point can be moved to be as close as possible so that they're almost exactly identical to each other, then we'll have a tangent line. And so that's the idea behind differential calculus, that idea of we can find a tangent line by starting with a secant line and letting that distance between the 2 points get as close to 0 as possible. That idea of getting as close to 0 as possible, that's going to be a big idea that we're going to talk about throughout this chapter. The other big problem that we had in mathematics that we wanted to solve was the area problem. If you have a nice shape like a triangle or a rectangle, finding areas is not difficult, but suppose you had a funny shape like this function 1 over x, and you wanted to find out what's the area underneath that curve. What's the area between that curve f of x and that x-axis? That's not a nice shape, so you can't easily find that area with a formula. So instead you might think about trying the following. You might say, well, I'll start by making little rectangles. And if I made a rectangle that went from 1 to 2 and a rectangle from 1 to 3, and I had my height for my rectangle being the y value, for x being 1 and the y value for when x is 2, I would get something that would be close to the area. It would be a little bit too big. I would have a little bit extra and a little bit extra. So what I would find for the area of those two rectangles, it would be a little bit larger than the area under the curve of 1 over x, but relatively close. If I went for more rectangles than 2, if I made 4 rectangles, then the amount of extra that I would have would be a little bit less. And if I went even wilder and went with 8 rectangles, then the amount of extra that I have is even smaller. As I make my rectangles narrower and narrower, the area of the rectangles becomes closer and closer to the area underneath that curve. Again, this whole idea of things being closer to 0 comes back. What am I doing here? I'm taking my rectangles, and yes, I'm increasing how many rectangles I have, but that means that the width of each of my rectangles is getting smaller. Originally, I had widths of my rectangles of 1 unit, then 1/2, then 1/4, and if I let the width of my rectangles get as close to 0 as possible, then I'll have no extra amount. I'll have that the area of under the curve will be the same as the area of all of those little rectangles. Of course, we have to talk about what does that mean, getting as close to 0 as possible. And so that's going to be the topic of our next section. What do we mean by as close to as possible? What does it mean to be as small as possible?